instructor for the session. And I think before I jump in, let me mention it and emphasize this again. And even though this is very obvious, this session is for you. And so feel free to ask any questions you have. I'd be happy to answer any questions that I can field during the presentation period. Sometimes the questions have a longer answer. I'll try to attempt and answer those as well. But don't be shy. I think this tutorial is precisely for you. And if you hold back your questions, it basically, you're not doing justice to yourself by attending this session. So please feel free to ask. Don't think that the question is too simple or too complicated. If you have a question, very likely others also have this question or similar question. And I have done this tutorial for over, a dozen years. So, it's always, great to hear those the questions from the attendees, and many of the times they are similar ones which are lurking in other people's mind as well. So with that, let's get started. I'm going to do a shortish lecture because we are, like I mentioned, we are a little short on the session duration for this one, and then we'll jump into the hands-on section exercise for most of the tutorial. Okay, so let's see. I posted a link to a web page which I have for this tutorial. Of course, if you have the repository, all the information is there as well. So let's see. Share my screen here. And I have to turn my video off because my computer doesn't like screen sharing and video at the same time. All right, can you folks see my slides?
Yes, we can.
Okay, perfect. All right, so let's jump in. Okay, so this tutorial is geared towards beginners who generally folks who have not really used Visit visualization software, but if you have used it a little, I think you'll still benefit from it. But if you know Visit visualization software, to an intermediate degree, there may be only one or two nuggets that that you may be able to find useful here. So I just want to preface that before you invest time in attending this tutorial. And the goal really is to provide a background of standard visualization techniques that are used for mesh-based data. Also share a few application scenarios, and we'll do all these visualization techniques hands-on in the Visit in the hands-on session using the Visit software, and also mention some best practices and things like that. So I normally have a sort of a longer lecture, but I'll do a shorter one, and then we'll spend most of the time in the hands-on session. But before I jump into that sort of thing, let me bring up a few things that you must have. If you haven't already downloaded, you should download, actually this is slightly, you should download version Visit 3.1.4. This is not the latest version, or is it? And the reason for that is we have a profile on. Later on, we will be using the remote visualization, and you need a specific version. Let me actually double check here, and I don't want to give you wrong instructions. I think I posted them in the right version on the repository. I just want to make sure that I'm not giving you the wrong information. And that is something you will absolutely need for this tutorial if you don't have that set up yet. So I think it's in the preparation. Yeah, preparation document is where it is. Yeah, okay. Yeah, it's 3.1.4 is what you should download. And you should grab the data and other things as well. So if you, I'm going to put this thing in Slack as well, so you have access to this quickly. So if you don't already have that, you should install that particular version and download all those things while, I go through some of this lecture stuff. So let me just jump closely to these techniques. Okay, so let's talk about visualization techniques, at least the common ones that we encounter routinely. So here are a set of visualization techniques which are used, somewhat at a higher frequency with mesh-based data. And the ones in the bold, we will actually do it as a hands-on exercise during the visits hands-on session. Okay. So one of the technique is called color map, or pseudo color map, or pseudo color plot, as Visit likes to call them. And in this technique, the idea is, let's say you have data, scalar data, that means one-dimensional data, and you or a single variable data is a better way to say that. And then you want to map it to a color table. Also, you could think of this as a heat map, if you will. And this kind of technique is very, very powerful. It allows you to easily investigate the range of the data. You can quickly see the spread of the data. And it's great for error diagnostics and quick visual validation. So here is an example of a color map or a pseudo color plot. In this case, there is a lot going on. So you see that there is a map which has been overlaid onto the visualization. You can see there is a little bit of bumpiness onto the picture as well. But then more importantly, there is the color associated with the entire 2D area of this this earthquake simulation, where it shows the ground acceleration that happened during the course of the earthquake. And so you can see the regions that shook heavily in kind of deep red, and the regions that were not affected in kind of teal blue, sort of a green color, and then everything in between. And this is great to kind of assess, the range of the data, or at least the scale of the data. And then sometimes when you're writing code or using somebody else's code, sometimes, errors can happen due to various reasons, and the data can produce unpredictable or out of the range values. And sometimes those are very hard to find, but with this sort of technique, sometimes you can pull them out pretty easily. So this is great for error diagnostics as well. The next technique is a geometric technique, and the idea is to either identify regions with the scalar value or same value or single value. And the way to do that is, if you are working with two-dimensional data, you can draw contours onto that data. But if you are working on three-dimensional data, you can create isosurfaces. And isosurfaces are nothing but contours in 3 dimensions. The word isosurface is a conjugate of iso, meaning same, and surface is a surface. So surface of a constant value is an isosurface. And then another method for using the underlying geometry is explicitly draw the geometry the way it is. So let's say if you're working with triangular mesh or a tetrahedral mesh, you can just draw it as is and then color it based on some properties, like some variables and things like that. And so here is an example of a 2D data, which has been shown in color map, but then you also see those concentric rings. Those are essentially your contours at different values. We see this sort of thing in, topographic maps. If you go for tracking, you will see that, what the elevation is. And, you'll see these concentric rings, which are at constant values. And then if you take this idea of contours into 3 dimensions, you can get isosurfaces. So here there are 10 isosurfaces being displayed at different values. They are shown in different color and opacity. And the idea is you can change these values interactively, so you get a different surface based on what that value you have chosen and where the surface may pass. And you'll get a more intuitive understanding of this once we play with Visit. And then the last idea was to draw explicit geometry as is. And so here we see a couple of pictures at the bottom of the screen where, you have on the bottom left over here, you have a space shuttle, which is essentially trying to show the geometry of it. And then you also have, an airflow being represented with this purple and yellow color. And you can see that there is also a vehicle where it also shows the airflow along the body of the vehicle. And it's all shown in the geometric form, right? So you can see, more or less the triangles or the tetrahedras, drawn as computed by the simulation. And the idea here is these kind of things, when you're working with unstructured data or irregular data, it's very important to kind of know what's happening at boundaries. Sometimes you get pinching or a tear in a surface, and that can produce unpredictable results with the numerical solvers, because they have some assumptions about the boundary conditions, and you really need to make sure that the mesh is of high quality and it blends in where you expect it to blend. It's not tearing or pinching and things like that. And while there are numerical measures to kind of assess the quality of mesh, it's sometimes much more easier to visually inspect the mesh and make sure the problematic surfaces are blending correctly and things like that. Yet another technique is volumetric technique. With the geometric technique, you only see the outside of something. On the contrary, with volumetric technique, it's primarily used to inspect something on the inside of a volume. And the idea is, if you have a single dimensional variable or a scalar data, then you map it to a transfer function, which is essentially a combination of color and opacity. And if you use this transfer function to render the image for the data, you get a picture, which is what we call volumetric rendering, and it represents what's inside the volume. And this kind of technique is very useful to see the inside, obviously, of the volume, but it also depicts what may be happening inside the volume, depending on what type of data there is. So if you see here, many times these kind of pictures look many times these pictures look pretty stunning, and they are often created by this sort of technique called ray casting, and where you shoot the rays into the volume, and then the rays intersect at various places in the volume. You compute the color and opacity, and compute the resultant color and paint it onto the image. And so in this case, this is a visualization of a star going supernova. So you see that the blue inside shell is the core, and then the translucent outside blue shell is the shock wave of the star. And then between the core and the shock wave outside, you see a complex explosion going on, which is represented by various colors. And so this sort of thing is very useful to understand what may be going on a bit inside the volume, and it can provide some very good insights about the phenomena that you are trying to examine. Yet another technique is streamlines, and this is mostly applied to the data which has a flow component to it. And the notion of streamlines is exactly the same as you would kind of understand from mathematics, which is, it's just a tangent to the velocity vector. So if you take a point and take a tangent of the velocity vector, that's what you get, a streamline. And it's instantaneous. That means it's at that same instance in time. And that's useful to investigate the nature of flow. So if you pause a hurricane and trace a point and see where it's pointing and keep connecting those with a line, you get these kind of a spaghetti sort of lines. And this, if you seeded the points correctly, you would be able to see the sort of eye of the storm. So on the left side, that's a volcano visualization, or not volcano, sorry, tornado visualization. And on the right side, there is a spacecraft. And you see two vortices being formed on the wings of the aircraft, and you can see that. One issue with this sort of technique is that you have to seed the points more or less in the right spot to get these streamlines populated properly. And it's also computationally pretty expensive. If you have lots of seeds, you can get many of the lines, but the problem is that you end up with a spaghetti, so you cannot see very well. If you have too few, you may miss the region of interest. So you have to experiment with this sort of technique quite a bit to actually get the desired result. Similar technique for flow is LIC, which is a short for line integral convolution. And the idea here is to create a synthetic version of the data by, let's say you have a 2D mesh which has a scalar data on it or a single dimensional data on it. And what you do is you convolve it with some sort of a synthetic noise, like a Perlin noise or something like that. And you get this, this kind of a gradient, which you can plot in grayscale. And this essentially enriches the flow field. And you can see this, these vortices and the structure of the flow very easily. But this is synthetic, right? This is not the real data, but it tells you the nature of flow. And to give you some intuition about this, and the idea of this is like, let's say if you have a pan and we put some sand on that pan and we tap the pan from below, after a while, we'll see some sort of patterns that may emerge because as a result of that tapping. And that's essentially what line integral convolution does. It basically creates these flow fields based on convolution of the data, based on an artificial synthetic noise, such as a Perlin noise. Another way to represent the data is by putting a glyph on any point. And we are very familiar with, if you have a vector data, you can put like an arrow glyph to show the direction of a vector and the magnitude of the vector, and you can color them with the magnitude, and you get something like which is shown on the right side with the yellow and red arrows. But on the left side, you can take the same idea. Instead of drawing arrows, you can draw ellipsoids, which basically encapsulate the minimum, medium, and major axes of the vector, in this case, a three-dimensional vector, and orient it in the direction of vector and show it that way. And so this is, again, useful to investigate the flow of the vector data. And then we have topological techniques, and these are more useful for flow sort of thing. And the idea is to investigate, the critical points of the data, which could be a local minima, maxima, or saddle points. And so this is essentially a construct, a math construct, in which you compute the topology of the given data and construct this network. And if you look at this right panel here, it shows this kind of a stepped lines and this yellow and red circles, which depict the various critical points in that volume. And the idea is to construct this graph. And then once you have constructed this graph, you can show it in combination with another visualizations overlaid or on top of it. So in this case, on left side, you are seeing a volumetric rendering. I think this is, again, some sort of an astrophysics simulation, and then you compute this topological structure, and then you overlay the volumetric visualization on top of it. And now you can again see where those critical points are happening into the volume. I'm going to skip the tensor one, but if you're interested, you are welcome to take a look at those papers. This is again trying to represent 9 variables in 2 dimensions in a visual form. So it's it requires quite a bit of coffee and thinking and seeing how it's being mapped. So I'm going to skip that for now. Another technique which is comes from information visualization side of things is parallel coordinates. And the idea is, like, if you have more than 2-dimensional data or multidimensional data, how do you represent it? And in that case, the idea is, if you see this right picture at the bottom of the screen, you see there are multiple axes. Each axis represents a different variable. And the idea is you connect each variable along each axis, along each cell with a line. And once you connect all these axes, all the points line, cell-wise, you get a maze of lines. And this is essentially a parallel coordinate. And then you see something highlighted in red is essentially if you constrain and select only a portion of one axis, it highlights the range of those values constrained along the entire axes, all axes. So we will see an example of this in Visit, where we'll constrain some things along one axis, and it will highlight all those cells in other regions as well. And so there are many other visualization techniques, that are out there, but some of these are the ones we will cover today. And so this was the example of the parallel coordinate again. So if you have high-dimensional data, you create multiple axes, one for each variable, and you get these cell-wise connection will give you a maze of line. And then if you constrain it, like in this picture, if you look at the bottom right, you see that the last axis is being constrained in a smaller top region, and then the cells from those regions are highlighted across all other axes. Now, this is not just for this bottom panel, but what's also happening is once you kind of set up this sort of a constraint, you can actually apply it to other visualizations. So on the top, you have the visualization of, so this is a tokamak, which is simulating, nuclear fusion, and then this plasma spinning around. And what this bottom parallel coordinate is doing is it's saying, only show me the regions which meet this criteria. So you have these different variables along each axis, and you are saying that, show me where, the temperature is in this range, show me where the velocity is in this range. And so you can create these thresholds through the parallel coordinates, and then the visualization, you can apply the selection into the visualization. And you can actually see those thresholds kind of pull out and, filter out the data that is of interest, or, and highlight the areas that are of certain interest to you. And so this is a very powerful technique. In this way, you can combine filtering the data on multiple variables or multiple dimensions, but still see only 1 or 2 dimensions depicted by a plot type. And we will try this exercise with the different data in the hands-on session, so you get an intuitive a sense of this. Okay, so let's see how we are doing on time. Okay. All right, so let me mention some examples really quickly before we jump onto the hands-on portion. We all know that visualization is useful for communicating results and things like that. But let me emphasize the 2 other aspects which are not very well kind of used or understood. One of them is confirmation. I'm not sure if you folks have seen this data, but essentially it represents 4 pairs of XY data on XY, 2-dimensional data, and 4 pairs of them. And if you look at the statistics for all 4, they happen to be the same. So the mean for XY is same, correlation is same, and even the regression line is same. And if I were to ask a question, what would you conclude based on the statistics? It would be pretty hard pressed to kind of say that, these data are not that similar, but, it'd be easy to conclude that these data are kind of similar. And however, if we plot them, they are not actually similar. The distribution is very different. And so this is a contrived data set, and it was proposed by Enscombe, a statistician in 50 years back. And his take was that when you get the statistical measures, you still gotta go and look at the data to see whether your hypothesis is still right, because the data distribution may be very different than what you think it may be. And so that was his kind of a way of explaining that, you need another method to kind of confirm your hypothesis. And so visualization in some ways offers you that independent method of examining the data in a different way, either confirming or refuting your hypothesis that you may be working with. So, and I think now we have machine learning also in the mix. So if you look at machine learning, is statistics and visualization, they form kind of a trifecta, if you will, that you can try to use three methods independently of each other, sometimes even complementing each other to confirm or refute a hypothesis. So that is something very interesting that can be exploited for hypothesis confirmation or refutation. So let's take a look at application of visualization for inspection and exploration. And so here is an example. Let me play this video. And so here is, let it play back. Let me play it back another time. So here is again, okay. Here is a visualization of earthquake simulation. So earthquake starts somewhere in the middle, and then the wave more or less pushes towards the right side. And everything looks fine till like almost till halfway through, the ground waves kind of move in a kind of a sort of expected pattern. But then you see around at this time where I've frozen the video, you see something odd that is happening. The top boundary, there are waves coming out from the top boundary. You see that? So everything looks fine till here, and then boom, something comes out from the top. And so something bad is going on here. And what has happened is that these boundaries are supposed to be absorbing everything. And after a while, halfway through the simulation, the top boundary starts to reflect those waves, you see? And the reflections are actually in the same range as the real data itself, what it's trying to kind of model. And this sort of thing is very hard to figure out numerically because they are in the expected range. And so once we did the visualizations, the computational scientists went back and looked at the code and found that there were some errors with this boundary, and it starts leaking after some point and starts reflecting instead of absorbing. And so they fixed this code and to kind of get a better result of their simulation essentially, right? And this kind of thing is very hard to kind of catch also, but this is nothing but a color map with which you can very quickly find out these anomalies. Here are some other examples of of data. And so let's say if you're working with large pieces of data, and then you sort of do a domain decomposition to kind of distribute the data into multiple processing units and things like that. You want to make sure that the boundaries are well covered as you expect them to be. Sometimes there can be gaps between when you do the data sharding or break up the data into different pieces. The boundaries may not line up correctly, and that can create, odd artifacts and sometimes downright incorrect results. Same idea with if you're working with a mesh. If you see there is this triangular mesh on the top right side, and it's kind of nonlinear, non-uniform mesh, and these triangles are kind of very of different shapes and sizes. Sometimes there can be tiers, or sometimes there can be very small triangles with with big acute or small acute angles, that can create problems with the solvers. So sometimes those kind of things are very easily found through visualization and inspection. On the left side at the bottom, you see kind of a cube, which is showing kind of this red, blue, and white pattern. And this is actually the same data as the earthquake simulation, which I showed in the previous video. And in this one, what happened was the simulation wrote the data in some format, and then when we were doing some translation for analysis or changing the format of the data, there was a bug introduced in the code, and the loops for XYZ were kind of mixed. So instead of seeing earthquake-like pattern on the surface, we are seeing the data kind of mapped around in the entire volume, which you don't expect to see. And so sometimes these small bugs can introduce big problems, and they're pretty easy to inspect with this sort of color map sort of thing. Here is another example. Let me see if I can play the video. So here is kind of 9 panels of visualization on each side. If you look at the way to read this is, if you look at the first column, it's a simulation running on a CPU, and then there are 3 variables along each load, the Vx, Vy, and Vz. So this is velocity along X, Y, and Z directions. Again, this is for earthquake simulation. This was a very large earthquake simulation, and the idea was that GPUs were becoming very popular to port the simulation on GPU and see if it would run any faster. And so the middle row on the left side is the porting of the simulation from CPU to GPU architecture. And it sort of looks okay. And then the scientists thought that this was all, the porting was completed and it was working well, and it's actually running very fast. The idea was to kind of publish the results and do create some pictures for the paper and things like that. And so when we started looking into these results between CPU and GPU, you see for some part, the visualization kind of shows that there is, if you look at the first 2 panels on CPU and GPU and Vx, it looks okay. But if you look at Vy, you see that, that's quite different actually. The structure, overall structure is similar, but the local areas are not similar at all actually. And so you see quite a bit of variability between the CPU and GPU simulations. And if you look at the relative errors being plotted on the third column, you see that the areas being marked as white are more or less the same, but the black ones are the ones to worry about. So let's play this visual movie. And so once we kind of did this movie on the left side, we sent it back to the seismologist and the computational scientists that indeed that the simulations don't seem to be producing the same results or similar results. And after looking at this left movie, the seismologist said that this is not acceptable. We need to find the source of the problem and see where it is, airing out and fix those. And so once this problem was resolved, you see the same panel on the right side is the revised simulation. And now you can see, if you pause at any point, you can see that the CPU and GPU simulations actually more or less look quite similar. And then there is very little artifacts which are appearing on the relative errors, and there will be some. And that's due to the fact that the CPU and GPU architectures are inherently different. One of the things that was happening at that time, this was like 2009, 2010 timeframe, is that CPU, when you do a double compute a floating point and a double precession, CPUs will inherently compute things at 80-bit, even though you only see 64-bit. But GPUs only compute things at 64-bit. And so there is a difference between the floating point results, and that's why you see some speckling here. However, the other errors that they found were due to the fact that they found few kernels on the GPUs that were running in 32 bits when they should be running on 64 bits. They also found a division by zero error that was happening somewhere, and that was also a source of problem. So once they fixed those things, we did the visualization again, and then we saw that indeed the simulations create very, very similar results not necessarily identical, but very similar results. And so this is, again, nothing but a simple example of a color map. And you can see quite a bit of information out from that. Here is another example of a comparison. In here, this is a simulation from Mike Norman, our former director of SDSC, and he studies, evolution of galaxies, and this is his simulation where he tries to simulate how galaxies formed after Big Bang, and what they did was they added new physics to their simulation. So they added radiative transfer to their simulation and ran that simulation again with new physics and tried to compare the results. So here, what they did was the older simulation and the new simulation, they did a difference of the two data set at the same time snapshot, and then they did the visualization of that difference. So this is the volume rendering of that difference, and then you see that on the left side, they say that if you're looking at yellow stuff, that's the older simulation, which was non-radiative in nature. The teal and the bluish kind of stuff is where there is no difference. And the red stuff, which you're seeing, is the one which is the new physics, simulation with new physics is showing some differences, is the red stuff. And you do see that there's quite a bit of red stuff in there. And what they found from this was when you have considered the radiative transfer or the new physics, the galaxies actually evolved much faster than without the radiative transfer. And so this was their way of comparing their prior work with new work to kind of figure out what that difference actually leads to. I'm going to skip this one in the interest of time, and even this one. Okay, so let's talk about a few things here. A lot of when we write code, right? I mean, we write code to do some processing or do some analysis and things like that. When we write code, we can write a code, in a simple way and say, hey, do this, this, and this, and it works fine. But if you want to change this, your code, and do something else with it, then we really need to architect our code in such a way that we can break it apart and reuse pieces of it. And one way to do that is by employing a pattern called flow network. And the idea there is that you can read the data in a different operation and perform different operations as a different set of modules. And you can chain these operations together. So you are not rewriting previous pieces, and you are basically using modular software components again and again and chaining them together to produce results. And that notion is essentially flow network sort of stuff. And why this is meaningful is so here is your usual pipeline. You read the data, filter the data, and plot it. A fairly linear way of working with things. But if your software is structured in a different way, where you can read data from different pieces, combine them together using a filter, and then split them apart and do some plotting in different ways or analysis in different ways, this gives you a lot of flexibility to kind of do your analysis. And the reason to mention this here is Visit employs this sort of a data flow network underneath the hood, which gives it a lot of power and kind of doing a lot of things underneath the hood and reusing a lot of components for different things. So some best practices when you're working with visualization. While visualization, we often think that we are talking about creating pictures and things like that, and inherently those pictures have colors. But you got to be very, very careful with colors. And so the idea is to use the least amount of color you can. You can even try grayscale because our eyes are really good at picking up things at grayscale. We have like 100 times more rods, or maybe even 1,000 times more rods than cones in our visual system. And so we can see grayscale way better, or intensity of color way better than colors themselves. Try not to use the rainbow color map. It's being kind of phased out from many of the visualization packages. It used to be default. It doesn't quite work well. It's perceptually nonlinear, so don't use the rainbow color map. Try not to design color maps yourself. There is a good resource called colorbrewer.org or colorbrewer2.org. You can look at that and pick color maps from there. It's incredibly hard to actually design good color maps that will work well on a variety of devices and for a wide variety of people as well. When you're doing visualization, always include a legend, and this is easy to miss, in captions as well. And more importantly, and since we are talking about high performance computing, your data ideally should be written in a, if it's large, especially, it should be written in a parallel read-friendly format. And so there has been tremendous amount of work that's been done in this area. And try not to write your data in your own way, which nobody else knows how to read from. And so there are lots of libraries that are available that can write data in a parallel ready format. And you should employ those. NetCDF is very common in atmospheric communities. HDF5 is another format which is popular. And then there's a new format called Adios, which is very popular for simulation that are running at really, really large scale. And so those kind of parallel friendly formats are great to not only write your data, but once you use a standard library or well accepted or well used library, chances are the analysis packages already implement those formats for you, so you don't have to worry about reading the data into different packages. And so that's really critical. And also, when you're doing analysis, not just visualization, try to be as close to the data as possible. So the best time to visualize or analyze something is when the data is in memory, right? Once you write the data into the disk, you have to read it back. And when the data is small, it doesn't really matter. But as the data starts to grow, this becomes excruciatingly difficult. Sometimes the analysis and visualization of the data is more expensive than running the simulation themselves. So you really need to be careful on figuring out a strategy how to analyze or visualize your data. And that has an implication on the amount of compute cost that you need to allocate for analysis and visualization too. People routinely underestimate the time it will take for them to analyze the data, and they run out of either money or allocation time to analyze that data. So a lot of time is being spent and energy is spent in simulating something or modeling something, and then not enough computation time is sometimes available for doing analysis and things like that. So you gotta carefully understand your analysis and project those computation costs so that you can budget that compute allocation appropriately, whether you're asking for allocation from access or exceed, or you're budgeting it in your proposal or buying out time from somewhere else. Compute time is what I mean here. Okay, so let's jump onto the hands-on session, and let's go and talk a little bit about Visit. Let me see if there are any questions. Doesn't look like.
Amit, there is one question in the help desk string.
Okay, let's see.
Mahidar had jumped in and answered the question, but an additional question on this string was
okay.
how one runs it on CPU or GPU.
Okay. All right. So first question is, so do we set up Visit on Expanse? No, you just only set up on your local computer. We have already set it up on Expanse, so you don't have to do that. And the other question was, Susan, can you repeat that, please? How do you run on CPU or GPU? Yeah. So
this was Anna. Do we set up Visit on Expanse or on computers? And
right.
Mahidar had jumped in with the tutorial. requirements and on Expanse. And then the additional question specifically for you was the one running on CPU or GPU.
Yeah, so okay, so that's a good question. When you're installing it on your laptop or desktop, Visit will figure it out what to use when. You don't have to kind of do anything special. Visit will use CPU or GPU depending on what visualization model is being used or algorithm is being used, and it'll do that. And we can talk about that in the hands-on session too. On Expanse, we have set it up on CPUs explicitly for now, but it can be set up for GPUs as well. So there's a little bit of setup involved, and you know, so that's more of a cluster setup sort of thing. But on the desktop, you can set up the Visit application will take care of running either on CPU and GPU based on what it's trying to do. So hopefully that answers the question. Okay, any other questions before we jump into the hands-on session? And feel free to unmute. I don't know how many people are here, but feel free to unmute and ask a question if you like. Okay, going once, twice. All right, let's move on. Okay, so let's jump into Visit. I hope you folks have installed it. Just a couple of slides before we jump into the hands-on session. So Visit got developed at Livermore National Labs, and actually it was started out by an intern at that time, Hank Chives. And the way he wrote the software, scientists really liked it. That, you know, that model of doing visualization and analysis was really much more easier than anything they were using earlier. And the entire visualization team at Livermore got behind that idea and you know, rewrote the entire thing in developing this new architecture, which ended up being called Visit software. And so it is cross-platform. It can run on you know, your desktop, and it can run on, you know, supercomputers that are very, very large and run kind of, you know, non-traditional kind of operating systems also. So it can be compiled to, you know, IBM has AIX, and, you know, Cray has Cray Linux and all that kind of stuff. It can compile to those kind of architectures as well. And it's, again, available as open source software under the BSD license. It has lots of support for reading different types of data. I was mentioning, don't try to write the data in your own format. Leverage the ways of, you know, using a library. I think this is a little old. I think by now Visit supports maybe like 130 different kind of data input formats. And one of the key strengths of Visit is that you can use it locally on your laptop. You can run it remotely on a supercomputer. But more importantly, you can actually run it as a client server. So where the client runs on the desktop and the computation happens on the cluster. And we'll try this out later on at the end of the session. And then it's again it supports large data, so it's scalable. I think these days it's routine to run Visit software at 100,000 cores, and which is kind of a marvel in itself to run such a complex code at that scale. And then you can use Visit software in three ways. You can interactively use it through the graphical user interface. You can read it through command line, interact with it through the command line interface, or you can batch it, meaning that you can just submit a job which does its thing and gives you the result. You don't do any interaction with it. It just runs as a batch software, which is suitable to run it on HPC machines. And then you can extend it by writing, you know, your own thing in variety of languages. So Visit is written in primarily C++, so you can extend it that way, but it also has Java bindings, and it also has a very nice Python API. And we'll play around with that very quickly in our hands-on session to kind of give you a flavor of it. And then, yeah, it's heavily used and it's continuously developed by the team now at, you know, they are at different labs now, not just at Livermore. and people contribute to it from different institutions now. Okay, so let's quickly review the visit architecture. This is slightly important to kind of get a grasp of this thing. So when you run visit, go ahead and start visit on your laptops or desktop. You would see that there are two things that are appearing on your screen, but in fact, there are four things that are there that are running on your computer. You'd see on a GUI, or the graphical user interface, or the main window on the left side. Then you'll see kind of a white canvas area. It'll be empty for you, which is the viewer. That's where the visualization or the plots will appear. Then you'll see two other things that are, you wouldn't see these two things. They are also running on your computer. One of them is called the database server. And this has nothing to do with the database like MySQL, Postgres, and so forth. This is nothing but a file manager, which basically tells visit which files are open, which are part of a set, and so forth. So it's just a file manager. And then you have a parallel compute server, or the compute engine. And this is essentially, a kernel or a snippet of code that is running on your computer, which actually produces the image. And so you see there are many of those. And so depending on how you're configured, you'll be running one or more of these. And then the idea is that when you run it on your laptop, everything runs on your laptop. But when you run in a client server mode, only the top two items run on your laptop, and the bottom two items actually go and run on a server or a cluster. And so that's how the client server communication then basically bridges the gaps between two. And visit takes care of talking to the server and bringing things back and forth. You don't have to worry about the transport part. Visit takes care of that. There is quite a bit of setup involved on the server side, which we are not going to get into. But if you're going to use a remote server, you can look at the documentation or ask for help how to set it up. We have already done the setup on Expanse, so you don't have to worry about the setup on Expanse. Now, once we kind of are looking at the user interface, so I'm going to be a little slow here and spend some time here, because this is something which we will be doing repeatedly again and again. So it's worthwhile spending some time here. So on the left side, this panel, or the GUI, or the main window, you would see, this is the area that you will routinely use to kind of, open and close different data files, set up plots of different types, add any operators to the plots, and then change any attributes that you want for a plot, like color map, range, and things like that. And once you're done that, you'd get a picture on the right side, which is appearing on the on this black background. And on the right side, you'd be able to, which is called a viewer, you can actually turn this thing around and see it from different angles. You're only seeing one viewer here, but actually you can have up to 16. So you can have different plots appearing on each window, and you'll see there are some toolbars and things like that, and we'll make use of those quite a bit. So on the main window, or the GUI window, you would see that there are file controls like open, close, the animation controls. Let's say you open a file which is numbered from 1 to 100. If it's a set, you would see these VCR-like controls. They only appear if visit detects a pattern of multiple steps there, then you'll see that. Otherwise, you wouldn't see it. Then you have plot controls, the add, operator, delete, hide, and show and draw. That's where you will spend time in kind of adding different type of plots and adding different type of operators. Anything you add will appear in this this window. It shows the plot list. And then you have this notepad area where you can actually put in, dock different widgets there. So in this case, it's showing a widget which is showing that it's running on some Livermore machine here. but it could be anything here. And then the status bar will show a progress of something. If it's taking some time to compute something, you'll see it at the bottom. Okay. And so the recipe for visualizing data on visit is fairly simple for the most part. The idea is you'll open a file. The misnomer here is open a database, which is essentially opening a file or a set of files. You create a plot of certain type. You set an attribute for a plot. Let's say you choose the pseudo color plot, which is called the color plot. You say, okay, I want to use this color. I only want you to show this range. That will be the attribute. Then you can set up some operators. Think of operators as filters and say that filter the data and only show me the data at this level, or do something else with the data, mirror the data, translate the data, copy the data, or something like that. You can do that with operators. And then you set the operator attributes, meaning, if you're thresholding the data, you would say what range you want to threshold the data and which variable. And then you change and refine the view. And essentially, this is what you will be doing pretty much with most of the most different type of plots that we will be doing with visit. So that's kind of the recipe. Okay, and I'll come back to this slide in a moment. So let's go and fire up visit. Okay, visit is here. So I'm going to be running version 3.1.4. Okay, you folks have it? All right. So once okay, I'm going to move these files to my home directory or your desktop. I think home directory, I'll move it on my desktop. And so if you look in the data files, you'd see there are lots of files in there. In the file which we will be primarily working would be a file called noise.silo. So it's in silo format. And I'll explain that in a moment once you open that, what that file looks like. But then you see that there is a set of files also in silo format called wave 000. And, it has, almost like 70 files or 71 files. And what visit can do is can group these things, and then they can appear as an animation. And so we'll look at that in a moment as well. Okay, so the first thing we are going to go and do is open. You can go from here, file open, or you can click on this icon. So I will perform these steps repeatedly and be very slow. So please bear with me, because I know you folks will be trying to do this while I'm talking, and you're trying to listen and see also at the same time. So I'll repeat several times. But if you miss something, if you want me to repeat it again, please do let me know. So open the file. I'm going to say click open. And I'm going to go to my desktop. Okay, so you may get an error like this. And that has to do with, I think if you're on a Mac, you can get an error like that. And that has to do with the permissions on a Mac. Normally, applications can no longer now read into different directories. To easily solve that, for now, I'm going to move this to my home directory, because actually I already have something in my home directory. So I'm going to read it from there instead of going and setting up those permissions right now. So I already have a directory, visit data files, in my home directory. So I can see that. If I want to go up a directory, you can see it says go up one directory. And so in this directory called visit data files, and I'm going to go and look for this file called noise.silo. Okay, so while we are here, there are a couple things to look at. If I scroll down, you see that visit is actually starting to group these things. You see, I showed you this file called wave some number.silo. It has 71 files and visit is grouping them. And if I turn off the file grouping, it wouldn't group them anymore. But if I turn it on, it will figure out grouping based on the file names and group them. And this allows you to quickly kind of load up all these files in one go rather than writing a separate file describing that all these files are part of one thing, and then it will read it. So it allows you to do that sort of thing very easily. Also, to kind of take a look here is open file type as. If I click on this thing, this is what I was saying earlier, that if your data is written out in one sort of a standard library or a well-known library, Visit can already read it. And so this is over 100 plus file formats which Visit supports. And so if you write out your files in one of these formats, chances are you don't have to do too much work to get it into the Visit. So I'm going to go and choose the file called noise.silo and open it. So click OK. Okay. Once you open the file, nothing will really happen except for the fact you will have noise.silo showing up as active source. Okay. Now, since we have loaded up this file, let's talk a little bit about it. So I'm going to go to File and then go to File Information. And this will give me a dialog box telling me the metadata about this file. So the way I got this was I opened the file first. Let me close it, do it again. So choose Open, go to the Visit Data Files directory, choose noise.silo. Once it's open, it will show up in active source. Then I go to the File menu, and then in the File menu, I'll click on File Information. And this will give me the metadata about this file. And so we'll see a bunch of things that are there. We are saying that there is a mesh of some sort. In fact, there are two types of meshes. One is called a mesh, and another thing is called mesh is 2D. It has some spatial dimensions. Spatial dimension is 3. The mesh type is rectilinear mesh. And it has some coordinate. It goes from -10, 10 to -10, 10. So now those are the coordinates. It has some unit in X, Y, and Z. And it has some other things associated with it. I'm going to skip the mesh 2D and point mesh here for now. Then it has some scalars, which is essentially variables that are sitting on the mesh. It has different kind of variables. Let's look at one of the variable called Shepherd Global. It lives on a mesh called mesh. Its centering is node. We'll talk about that in a moment. Its units are joules. And it tells us some other properties around it. Let's look at another one. Then it has some sort of vectors also embedded in this mesh. One of them is called gradient or grad. Again, it's sitting on the mesh, and it's also node centered, and the units are centimeters per second. And then it has materials and things like that. So the Silo format is defined from, there is a library called Silo. It comes from Livermore. It allows you to package a lot of information in a single file. It allows you to define a mesh. It allows you to add different variables in that mesh of different type and associate them with the mesh, and then you can read it. So it's a binary. It's not a, if you try to open this file in a text editor, you will get a garbled output. It's a binary format files. So it writes it in as a binary, zeros and ones, and the library knows how to parse it and get this information out of it. And so that's essentially what this file is. Now, this file is totally made up. It's a bogus file. It doesn't mean anything, but it's good for tutorials. For many years, I've thought of replacing it with something else, but I think I have not been able to come up with something better than this. So actually, this works pretty good for tutorial perspective, and that's why it was created. So once you have this file open, what we can do is add a plot, and we are going to go and add a plot called pseudo-color plot, and then we're going to choose Hardy Global. So once you go to pseudo-color plot, it will show you all the variables that are available that are scalar in nature or single dimension, and we will choose the variable called Hardy Global. And if you click on it, you may or may not get this picture. And so if you don't get a picture, you have to click draw. And if you already have this picture, that means, you know, things are already drawn for you. And so what you can also do is, if you don't already have, turn this on, auto apply, turn the auto apply turned on, checked on. And that way you don't have to click draw every time. If you have this unchecked, every time I add a plot, I have to then click draw. So if I check auto apply, I don't have to click draw. So the changes are instantaneous. Okay, so I think we are coming to our break time. So I'm gonna just wrap up here and then we'll do a break. So how about we break at 9:20 and they take a 10-minute break, okay? But let me kind of show you a few things since we are here. In this kind of visit case, I hope you have a mouse so you can interact with this thing easily. And the way to interact with this thing is if you press the left mouse button and drag it, you can actually rotate the cube. So if you press the left mouse button and keep it pressed and drag the mouse, you can rotate the cube. If you have a wheel on your mouse, you can turn the wheel one way and the other. It will zoom in and zoom out. If you're on a laptop, you can do the pinch in and pinch out to kind of zoom in and zoom out. And then sometimes you can get lost like this, okay? Like really gone, don't know where things are. Then you can right click and choose reset view option, and it will bring you back to the top view. And then there's one last trick to this thing, and this is something easily forgotten. And if you press the shift key on your keyboard and then press your left mouse button and then you move, then you can pan. So keep the shift key pressed on the keyboard, then press the left mouse key and then drag, and that way you can pan. Okay. So if you keep your left mouse pressed and drag, you can rotate. But if you press the shift key and press the left mouse key, you can actually translate or pan around the scene. And then with a zoom, the scroll bar, the scroll wheel, you can zoom in and zoom out. So you can hide a plot by clicking on this hide button, show it. You can delete a plot by pressing the delete button. Let me add it again. So what I did was add pseudo color Hardy Global. That's the variable which we are plotting. We get something like this. So let me do this from the top. So once I fired up visit application, I chose open. Then I went to this folder which we downloaded, which is in my home directory called visit data files. I chose noise.silo file. When I open it, nothing really happens because we haven't added any plots yet. Then we go and add a plot type called pseudo color and choose Hardy Global as the variable that we will be plotting, because there are many variables available, but we'll be plotting Hardy Global. And once we get, if you don't get anything plotted, you press the draw button. Make sure you have auto apply turned on. And then if you press the left mouse button, you can navigate and rotate the cube around. Okay. How are you guys holding up? Let me hear some verbal answers to see if you guys are still around.
We do have a couple questions.
Okay, let's see what they have, what they are.
Starting in the main room.
Okay.
Could you repeat why it's better not to use rainbow color map?
Okay. All right, so we can get to that. I'm unable to choose the path in the visit directory. Can you move it to the home directory? Move the folder to your home directory, and then you should be able to open it. Oh, you got it. Okay. Okay, so the question is, why not use a rainbow color map? Let's see. Let me see if my slides still have that link. So this has to essentially do with the perceptual uniformity of the colors. Not sure if this will open or not. Okay. So I think this is the main reason. So if you plot the rainbow color map in grayscale, this is what you get. Okay. And you think like it's going from light to dark, but it's not really going from light to dark. If you look at the segmented colors here, you see it's going from white to light gray to dark gray to lighter gray and black, and then dark gray or black almost. That's what the rainbow color map does. And there is a problem, right? There is a dark gray coming before the light gray. It's inserted between two. And our eyes, the way our visual system works, we are so tuned to intensity, you see, that you can get these bands and you can actually think that something is important when it's really not important. So this has to do with perception, and you're welcome to kind of, read this article, but essentially that's the idea. So when you are designing color maps, the idea is if there is a magnitude associated with something, you basically kind of choose a color scheme that kind of goes from dark to light or light to dark, if there is a magnitude associated with something, which is often the case in many of the visualization which we work with. So that's the reason. So let me post this here. And maybe make a comment here. Oh. All right, so I'll make a comment here, but so let's break, and then we will resume at 30 after. So it's 9:21 right now in Pacific time, so we will meet at 9:30. So if you're on East Coast, we will meet at 12:30. If you're in Midwest, we'll meet at 11:30, and if you're Mountain time, I guess, we meet at 10:30. Okay, so let's take a short break, and then we'll resume from there. So make sure to stretch because it's going to be pretty intense next hour. So make sure you have walked around a little bit and take a break. Don't work with visit right now. We'll get plenty of time to work in the next hour. Okay, so visit and do a plot type. Let's add one more plot type. If we click on add, and then we add another pseudo color plot call, and then this time we're going to add shepherd logo here. We get another one. Now we have two plots going on at the same time. Now there is a problem, right? Because it's the same area occupied by both plots. And so I'm going to hide one of them. Let's hide both of them and then unhide one of them so we can see it. So you can have multiple plots going on, although you have to be careful that they don't overlap with each other, then you wouldn't be able to see it. So let's do, I'm going to get rid of both of them and do it again. So I'm going to go and add a plot called pseudo color and then choose Hardy Global. In the next plot, I'm going to choose a different type of plot called contour plot for the same variable called Hardy Global. Okay, so I get a different plot in there. Now if I hide the first plot, I get I can see the second one going on here. Okay, so let that be hidden. And so what's going on here is, actually I need to go back, sorry. I need to go back and explain you a few other things before we jump in this far. So let's go back and just work with our Hardy global plot here. Okay, so now we got a plot here, but it's not in the color which we want. It's not in the range that we want. How do we change that, right? So double click the plot and you will get the plot attribute window, something like this. And it is telling us a few things. The first thing which we want to change is maybe change the color. We'll change the color, and if visit comes with all these different color maps, you can add your own color map also, where you can pick any one you like. And then what we can also do is, by default, when you visit reads the data, it will go and find out the minima and maxima for that data, and it will actually show that in the legend. But let's say if I don't want my data to be colored from the minimum to maximum, I can say minimum should be 2 and maximum should be 4 and hit apply. And now, even though the minimum and maximum are 1 and almost 6, our color range only goes from 2 to 4. Anything lower than 2 is going to be whitish. Anything more than 4 is going to be this dark magenta-ish. So that's how you can change your plot colors. Also, if you want to plot the data in log scale, I can simply choose log instead of linear, and now my data will be plotting in log scale. In this case, it may not matter as much because the range is fairly small. There is another thing called skew. If I choose skew and choose like 10, you see that bulk of the data that is being plotted now is whitish. Basically, what's happening is amplifying the lower range and compressing the higher range. So this is not a log, and if I do anything below 1, like if I do 0.1, it will do the opposite. It will compress the lower range of the data and amplify the higher range of the data. And that's a quick way to investigate data at different. Sometimes the colors are not enough to pull out the range. And this is what the skew function does. The skew function essentially maps this kind of, if it's 1, it's just linear. But if you do anything below 1, it will basically create these curves that will amplify the higher range and compress the lower range. But if you give anything more than 1, it will do the opposite. It will compress the higher range and expand the lower range. Okay, so that's very useful sometimes. I think when we were inspecting the file, so let me open that again. File information. We were seeing something which says, let's go to one of the thing here. Yeah, Hardy global variable. It's type mesh and it's node centered. You see node centered. What is this node centered thing? So if you notice that here also centering is original. If I click nodal, nothing will really change. But if I click zonal, see, it gets all faceted. You see? It's no longer interpolating. But if I choose nodal, you get a smooth surface. When things are zonal, that essentially means things are centered around a zone. If a cell is a zone, then maybe the value is centered right in the middle of the cell instead of on the vertices. When it's nodal, it's actually on the vertice. And when visit will interpolate the data when it's sitting on a vertex or a node, but when it's zonal, it will not interpolate this data. Now, zones doesn't necessarily need to be a cell. The zone can be any shape, right? Which is defined by your mesh. So your zone can be arbitrarily shaped, and you can have data on it as well. So that's why the zones don't get interpolated, because they can have weird shapes. Okay, and then there is a nice trick here. You can invert the color map also by checking on this invert box. You can also assign some opacity to the color map. Like here, I've made it, sort of, ramp, which is kind of 0 to 1. The lowest thing is translucent. The upper thing is opaque. and I can change it to a different ways. Okay, so that's where you will be setting up your properties of any plot type. If you double click the plot type, you'll get its attributes. Okay, so now let's hide this one and or delete this one. And now let's go to contour plot. So I'm going to go and add a contour plot. So to delete a plot, you just select it, right? And when you select a plot, it becomes blue. And when a plot is drawn, it becomes black. And when the plot is not drawn, it becomes green. So let me show you this real quick. So when a plot is ready to be drawn, it shows up as green. You see that? And when it's already drawn, it's either black or white. The text color changes. And if there is an error, it will become red. And so we'll show that in a moment, an error also. Okay, so let's go back and add a plot type called contour plot for the same variable. And see, it's not yet drawn, so it's showing up green. I'm going to click auto apply and hit apply. Okay, so now, okay, I think my computer has frozen. Okay, good. It's back. Okay, so now we have a contour plot going on. This is pretty busy. But now if we look at the legend, it goes ahead and finds out the same minima and maxima, which is essentially the same data. And then it's creating these surfaces. 10 surfaces are being created, and all these are marked by the legend on which color correspond to which value. So now if we double click this thing, we get the contour plot attribute window, and see by default it has an n level of 10. Let's change that to 1. And if I click apply, we only get a single value. Actually, let's do 2. If I do 2, then I get 2 isosurfaces of 2 colors. One of them is at 2 point something, and the other one, the green one, is at 4.2 something. So when we do n, visit will automatically segment these pieces into 2 pieces and give us the third and 2/3 of the value. But sometimes like I said, we want to kind of set these things up so that they are not going into the minima and maxima, but operating at a fixed range. So if I set the minima and maxima to 2 and 4, then if I do 2 values, I'm getting, the minima and maxima essentially, right? But if I do 3, I would get a value of 2, 3, and 4. So one of them is at the lowest value, the other one is in the middle, the other one is at the highest value. Many times you don't want this. Many times what you want is a value. Most of the times you would say, I want an isosurface at a specific value, and I can add those. So now I have 3 isosurfaces going on at values I have chosen. And you just kind of enter those values by just separated by a space, and you can get that. You can also change the color. If you press on the color and you hit the left mouse button and keep holding it, you get this palette from which you can choose a color. You can also set the opacity for this using the slider, so you have some controls over there. Okay. Again, you have the log scale available to you if you want to use the log scale. It wouldn't matter in this case, the range is so small. So now we know how to do a contour plot as well. Actually, I'm going to set the opacity at 100%. Okay. So now we do that. Let's add an operator to this. So we select the plot, and then we click on slicing and choose a slice operator. So we select the plot, go to operators, go to slicing, and then choose the slice operator. Got it? And then we see this sort of thing appear. So what happened here? If I pull this down, you can see that the slice operator has been inserted in the contour plot. If I double click that slice thing, I get the operator attribute, and I will uncheck this project to 2D. And now I can see that there is indeed a slice happening somewhere here. Okay. And I can make this interactive, and I can choose % here and move the slice down. So I can position the slice wherever I want by just moving it. And like we discussed earlier, isosurfaces and contours are the same thing in different dimensions. So we are projecting a 3D contour onto a 2D surface, you get these lines. And that's what is happening here. Actually, I'll give you a better intuition of this in another plot. So let's go back and delete this and add a new plot with pseudo color Hardy Global. And in Hardy Global, let's add a slice through the operator. You get this 2D picture. So now we are looking at a slice, and I'm going to double click the slice and uncheck project to 2D so we can still see the 3D. And now we can see that our slice is actually located at origin, right? But I can change the intercept to another value manually and change the location of the slice, right? I can slice along different axes, X, Y, or Z. There are different ways to specify where the slice is. So here I'm moving it along the axes using %. But what if you want to orient the slice along a non-orthogonal axis? To do that, when you're in the slice mode, this tool becomes available. You see here the one which has a plane and a normal jutting out of the plane next to the cube. If I click on this, we have these red handles that become available. With this, we can actually orient the slice any way we like. And it will actually intersect the data, pull out that data for us, and plot that for us. And this tool is only available when you are in this 3D slice mode. To get out of it, you just uncheck it, and then you can navigate. Okay? So that's a slice operator. You guys have it? So I'm going to reset. So if you look at any of the attributes that has the reset button too, I'm going to reset that. And so now we get a nice 2D picture. Now, when you are in this 2D picture, so if you're in a slice mode, just reset it and you'll get to this 2D picture. If you don't have it, let me do it again. So we start at the same level. So add a pseudo color plot, add a Hardy global variable to it, and then I choose a slice on it. This is what you should get. Once you are on a slice, let's say I want to find out the value of this thing in this red spot. The way to find out a value, obviously, is to read the legend. That's one way to do it. But if you want to precisely find out the value, there's a nice trick which Visit has. If you look at this +n, these are called pick modes. If I click on this area, Visit will introspect this cell and find out where this point is located, what is the node number, and more importantly, what is the value of it. I can add any number of pick points anywhere, and then Visit will find those out for me. So see, I'm dropping these points and Visit is finding these out for me. Same thing with +z. Instead of nodes, it's going to find out the zone. In this case, the zone is the entire cell. So it's telling me the entire 8 values of the cell, telling me the node numbers, and it's giving me the coordinates as well. Now, instead of +n, if I do a +s and drop a point somewhere, it gives me a spreadsheet. And in the spreadsheet, it will highlight which cell I'm looking at. So it will give me the entire 2D domain, and it will tell me what the plot point I have picked. It'll show me that. Now you can export this as a CSV file or something and, and do other things with it. You can even change the data from here and pick another one. So right now we are looking at Hardy Global. We can swap it and look at another variable. So I'm going to change it to grad magnitude and it'll give me something different. Okay. So those are pick modes. Now, to get out of this pick mode, you have to go and select. If you look at the screen, the viewport screen, you see this thing. There's an icon called compass. Looks like a compass, very hard to see. If you click on that, you'll get back into your normal mode. Since we are in 2D, we can't really do anything other than zoom in and zoom out. Now, let's say I want to get rid of all these spots. To do that, you have to right-click, clear, and then in clear, you would say clear pick points. Be careful. If you clear all the plots, it will delete it. You want to pick clear pick points. If you do that, it will remove that. Okay. All right, so let's do another one. I'm going to do a reset view so that I'm fitting back on the screen. Now, when you are in 2D mode, Visit also has this very nice feature. This is called a line out mode. If you look at this line out, this icon here, which looks like a XY plot with red and blue lines, if you click on that, what you can do is you can draw a line, press your left mouse button and keep it pressed and drag it, and then draw a line anywhere you like. So I drew a line. And what this will do is it will actually give me a plot of the values along that line. So it's giving me if I can draw multiple lines here, and Visit will actually plot those things for me. So I'm inspecting the value of something along a particular line. Okay, so this is grad magnitude. Actually, that's why it's a little not obvious, because it's plotting another thing instead of this thing. So let me change that real quick. Oh yeah, I'm plotting the spreadsheet instead of the other one. So let me delete the spreadsheet and let's plot it on Hardy Globals. And let's do the line out now, because that's what it was appearing. It was looking something weird. This is we're plotting those gradient magnitude instead of the variable which we want to see. And now we should see one peak. Yeah, it's in yellow color, so you can't see it very well. Let me draw another one. And you should see one peak here. Yeah, see, there we see a peak, right? So you can have multiple lines along any arbitrary axes, and you can have these plots here. And you can also export these out as CSV and things like that too. Okay, so we got the line out plot working. And we know how to add an operator too. And so I'm going to double click slice and uncheck this. So we see the slice in 3 dimensions. Instead of doing a slice in 2D, we can do 3 slices and actually remove this slice. Otherwise, you wouldn't see it. So we can get 3 slices in one row. You can also do a slice as a sphere. And this wouldn't make any sense. I'm going to remove this slice. You get a sphere. So you can create slices of different shapes, essentially, by using the slicing. Let's do a cone. Okay, so there's a conical slice. Uncheck to. Okay, so there's a conical slice. I had to just uncheck 2D, or you can do a cylindrical. Oh, that's just a mapping. All right, so you can do slices of different sorts. Now let's do one thing. I'm going to go back to a single slice. Okay, so this is now in 2D. I'm going to go and add an operator called transform. and choose the operator called elevate. And you should get something like this if you do that. So what it is doing is it is taking a slice and then pushing it based on the magnitude up or down. So if you elevate it, you get this sort of a landscape plot sort of thing. So it's turning a 2D plot into 3D. You can see the minima and maxima sometimes a little better in this way. Now, the order of the slices is important here. So first we are saying plot the Hardy global variable, which is a volumetric data. Then we are take a slice of it. So it pulls out a 2D slice. And then we are saying elevate the slice based on the data. And if you double click it, you can change a few things here again. So see, you can change the scale and so many things. You can do that. But if I change the order, if I bring the slice down and switch it, it will complain. And this time we see the text becomes red, there is an error. So now let's read this plot, what's happening again. We are loading the data and we have to read it from top to bottom. Then we are saying, take an elevation, apply the elevate operator to a 3D grid. Well, that's undefined. There is no elevate operator that we can mathematically define for a 3D grid to elevate something from 3D to 4D. We can't do that. And that's why there is an error. So the order of operators is important. So first you do a slice, you get a slice, you get a 2D slice, and now we can exaggerate the 2D slice into 3D. That's defined. And so that's what this is doing. So there are lots of operators available, and you can look at them. We won't play with each one of them right now, but you can get an idea of what operators are available. And you can apply these operators in different form and fashion. So let's do one more. I'm going to go and apply this transform operator and use actually selection and choose threshold. I'm going to choose threshold and nothing happens. If I click here, I can say I only want the values between 2 and 3. And what, okay, that doesn't look very interesting. Okay, so that's slightly interesting. So I can actually pull out the data that I want and filter out that I don't want. And I can do that in, multiple ways. So I can compose this now and say, in the Shepherd global variable, I want things between 1 and 3. So now we only get very little. You can add more and more variables and say, I only want certain pieces of the data in different variables, and Visit will filter out the data based on what you're doing here. So this is a little bit complicated, but the idea is you are only visualizing one variable, but filtering it on multiple variables. Does that make sense? Okay, so I'm going to remove this, and draw this. So now we are back to our simple plot, and I'm going to choose, I can swap out a variable on any plot and say, instead of visualizing Hardy globals, visualize Shepherd global, and see the plot changes a little bit. I can switch the variables to something else. Okay. All right, so now we know how to do a few things here. Let's do something. Let's do another type of plot before we do other things. I'm going to delete that. Let's go and do a vector plot. If you go to vector, you see only 2 variables are available here. So I'm going to do just the vector plot of grad, which is a gradient. And if I double click on that, it's plotting a fixed number. So I'm going to change that to 800. Uh-oh, my computer is not happy. Okay, so I plot 800. And then there is a way to dress this up a little bit more. I can say, okay, scale by magnitude. And you can dress this up in many ways. Okay, so you will get a much nicer looking picture. if you can set up these different properties. So that's a way to do a vector plot. Now, sometimes you want to kind of capture these images and save them for, including in reports, papers, and so forth. And you want to probably clean this up a little bit, like the annotation showing up here. To do that, you'd go to Controls and choose Annotation. And I don't recommend to do this ever, but I'm just going to show this to you for now. You can do no annotation, and it will remove everything. I'm going to reset it. When you're doing publication sort of pictures, you probably don't want the user information to be there. You can hide that. Sometimes you don't even want the database information or the file information. You can hide that. And then you can add many other things. So there's tons of control on what you can do here. You can even add some text. So that way you don't have to go and use Photoshop or PowerPoint to add some text. I can just position the text somewhere by giving it its coordinates and, write any annotation I want here. So it has decent level of control here on what you will show and see, and, you can control the size of text, how many they are, and on the axes and things like that. So that's how you will dress up an image or clean it up for annotation. Once you're happy with the sort of look and feel you want, you can go to File and choose Set Save Options. In Set Save Options, you would say where to output the file. I'm going to just output it in my home directory. I'm going to call my file as 123. And I can set the width and the height and so forth and the output type. You can choose all these kind of things. And then you can say Save and Dismiss. And when you do that, it will go and save your files in the home directory. I just called it 123. And here's my file. By default, Visit will pad 0000. You can change that, because if I save this file again, it will create the next number. It will not overwrite the file. Okay, so that's why that padding is there. So I think if I open this file again, yeah, so you see this gray background sort of thing because it doesn't have the background. That's why it's showing up like that. So that's how to kind of save the file. Now let's look at something more, one more plot type before we jump onto other things. Go to a plot called, and add a plot called volume. And I'm going to do a plot for Hardy Global. And this will take some time. And this is doing a volume rendering. If I double click, it shows default rendering. And I'm going to go to transfer function here. In the transfer function, I can actually press my left mouse button and start painting here, essentially. And what I'm doing is I'm saying that, only give me pieces of this data. So wherever I'm marking things as opaque, if the bar goes from top all the way to bottom to top, it's fully opaque. If it's less, then it's translucent, and wherever it doesn't exist, it's transparent, right? So I can change the opacity of these, and so this is showing the histogram of the data, okay? And now I can see whichever regions I want, I can see that. And then I can define different kind of color maps here. I can click on this thing and move the color and change my color table here. I can remove a knot. I can add a knot. If I right click on a knot, I can add a new color to that knot. And then I can define my color map. And same way as earlier, I can set up my minimum and maximum on what I want to investigate. So that's how you can get these volume renderings. So here, if I go to render options, and this is using default rendering, and this will use GPU, by the way, if you have one. And if I choose the raycasting to raycasting compositing, it will use CPU now, but it will create slightly different picture. See, it's taking a little bit of time now. A whole lot of time now. All right, so there we go. And so this is using raycasting compositing. And this can be very computationally expensive method. So you have to be really careful. You don't want to auto apply on when you're doing this, because anytime you change something, it will go and render, and that can take quite a while. So I made it opaque. It should render slightly faster. Okay, there we go. And anytime I rotate, it has to render again. So this can be very slow. So when you're on your desktop, you probably want default rendering. That way you are not spending too much time doing the setup. I'm going to switch the renderer. And so the default rendering is very fast, but lower quality. Okay, so that's volume rendering. Let's do one more thing here. So I'm going to go to Hardy Globals and just choose Hardy Global, pseudo color plot, just plot it. Let's go and add something here and go to controls and go to this thing called expressions. And in the expression, I can create a new expression. I'll just leave it like that. And I can multiply two variables. I can multiply Hardy Global times, any variable I have, I can multiply. And so I'm going to call it H2 fly. Okay, so there we go. We got H2. Okay, so I created a new expression here. But if you look here, Visit gives us an option to construct this through user interface too. So if I don't know my variables, I can go and select my user variables from here. I can go and choose a function as a math function. And you see there are tons of function here, like you can create your gradients, you can create or take a curl, or a curl of a vector, or create a gradient of a vector, or do other things. See, you can compute a lot of things. You can do a Laplacian. You can do many other things can be done here. So simply I'm going to just choose multiply for now, and I'm going to just multiply it with itself, and that's what. Okay, a little bit of typo there. Okay, there we go. Okay, so I have this expression. I can create any number of expressions here. And this is a scalar one-dimensional variable, but it can be multiple dimension and so forth. So now once I have this, remember we were plotting Hardy Global, but now once I created that variable, it's available to me. I just created this variable called H2. I can switch it. And so now I'm looking at the square of Hardy Global, whatever it was. But this data only gets computed when it's used. It will not get computed until it is used. So Visit will smartly manage the memory. It will only compute these at runtime, and it will not try to write this data out. So you can actually create different kind of derived data products right in Visit instead of creating them on a disk first, but you can just create them at runtime. Very powerful, this sort of thing. Okay, so that's that. Now let's look at another thing. I'm going to go to controls and go to command. If I go to command, you'll probably see everything empty here. I have a few things going on here. I'll clear it out. In this dialog box, I'm going to click record. Let me do that again. So what I did was I deleted all my plots. I went to controls and I chose, in fact, I'm going to close my database also. Then I choose command, and then I'm going to hit record. And it will prompt up, create this command line prompt and all that. You can hide that. I'm going to move this around here. I'm going to go back and do whatever we did from the top. So I'm going to go and open the file called noise.silo. Going to go and add a plot called pseudo color plot for the type hardy global variable. I'm going to rotate it once, okay? And then I'm going to go to control, command. I'm going to stop, okay? And when I do that, what Visit has done for me is actually it has given me the Python script for whatever operations I just did it manually. So I don't have to know the API. I can just introspect Visit through the user interface, and it will create the right commands for me in this interface. So I did open file, which is this command. Then I did a add plot, which is this command. Then I did draw plot, which automatically happened because I had auto apply on. And then I changed the view by turning the cube. So that's the view it has saved now. And so with this sort of thing, I can script things. So let me delete the plot, close the window. All I have is a script. And if I execute it, I get everything back, right? Let me clear this out and do one more time. I'll show you one more thing here. So I'm going to go and say controls, command, and record. And now I'm going to go and do things normally in the user interface. Open a file. This time open a pseudo color plot called Hardy Global. I'm going to go and change the minima and maxima to 2 and 4. And I'm going to turn it around like this. And then I'm going to go to the command and stop. And this time I'm going to get a lot. So what I did was I opened the file. I added a pseudo color plot, but now I'm adding pseudo. I'm going to delete this because I don't need it right now. And since I edited it a couple times, I think I have this going on 2 times. You see, this one is bogus. I'm going to delete that because it created when I was clicking minima and maxima. So I'm going to delete it. So now I'm setting up the pseudo color plot attributes. Most of the stuff I don't need. I turned on the minimum flag. I set it to 2. I turn on the maximum flag. See, it says max flag and turn it to 4. And the other stuff I don't even need. So I can just delete that. I can only keep the things that I want and make my code simple because I don't even need any of the other stuff. I'm not changing them. I'm not going to need them. So I just created the things that I need based on what I did. And now let's go back. This is what our picture looks like. I'm going to actually open a new window and run this here. And actually, I don't have the draw plot going on, so I better do that draw plot. Okay, there we go. So draw plot. And now, if I actually set the 2 windows side by side, you can see that the window 1 is the one we created by hand, but window 2 we actually created by code. So I actually deleted window 1. Let's create it again. So on window 1, let's run it again. And there we go. So I also actually created 2 windows here. And here's something cool that we can do. And I'll just do it for now, and then we'll do it together again for demonstration. So I have one variable being plotted, Shepherd Global, and the other variable being plotted in the other window. It would be nice if we can kind of, see them simultaneously in the same orientation. And you can, in fact, do that. If you look at this lock icon, I'm going to just turn that on both things. If I rotate one, it will rotate the other one. Okay. And there is no reason for this thing to have the same kind of plot. It can have any plot. So I'm going to go and add a contour plot. So now I'm looking at a contour plot for one variable in one window. And then I'm getting another window here with this sort of thing. So you can have up to 16 plots. You see, all these windows will generate, and all you have to do is change the active window and change the plots for that. So let's do this quickly. So normally we'd have kind of this sort of thing going on. What you can do is create a new window. If you look at the second icon here, which says, it has kind of a yellow star on it, create new viewer window, or you can create one from here, Windows New. If you do that, it may appear anywhere here. But what you can do is you can click on this 2 square box and it will kind of put them next to each other. Now in this one, I'm going to go and add a contour plot for Shepherd Global. And once you have that, you can click on this lock icon with an eye and it will sync the views for you. And then we can go and say save. In the set save options, you would have an option for tiled windows. And then what you can do is, I'm going to call this 222, save and dismiss. And when you have things like this kind of ready in Visit, when you save it, Visit will actually seamlessly blend them together. So you don't have to use Photoshop or PowerPoint to, paste things together. If you have it here, you can combine them here. Let me see if I have a movie that I can show you here. So let's see if I have one here. And we got to move on. We only have 15 minutes left. Oh, yeah, maybe this one. Yeah. Okay, so here is a visualization which I created. I'm going to forward this a little bit. So here is a visualization in which I'm just kind of rotating the visualization around. This is just a volume rendering. This is a geodynamo. Here are 3 windows. You saw that I created one. I have 3 here, and I have 3 different plot types going on here. And they are plotting different things. So this is kind of a sphere. I have cut out a wedge out of it so that you can see the inside of it. And let's move on a little further. And here I have 6 windows now going on. And they are all doing pseudo color plot sort of thing. And then you have contour laid out. And in one of them, there's the elevate operator applied. Remember we did this one? The elevate operator. And here's another one. So you can create these sort of things. In this case, actually, I should say that I think these are all time varying fields. So I'm not doing rotating around, but in fact, they are moving through a time step. So I'm just kind of creating a picture out of it. So let's do this real quick, this sort of thing. So I'm going to close out this thing, delete things here. I'm going to open and then choose this wave.stylo database or, set of files. If you choose these, this is a time varying data set, and I make sure that wave.stylo is my active source. And and if you go to pseudo color plot, now this has changed because this is a different file, and this is a tank simulation, and this has different variables. And so here's a pressure, and if I play this, so this simulation is actually modeling a wave in a tank. So the water moves up, hits the wall, and that's the entire simulation. So if I can go back and play this. And so here is a wave which gets created, okay? And I can actually go and create a movie out of it. If I go to File and do Save Movie, and it will give me a wizard. It will say what kind of movie I want and where I want it. I can add different kind of formats and then move them on here. I'm going to choose everything as default. And
output directory, I'm going to leave it as movie. I'm going to leave everything as default. And yeah, so there is a bug here, so it's not able to create the movie. But essentially what Visit would do is it will create this, whatever we are seeing on the screen, it will create that as a movie for us. Okay. So we'll get a movie like this created right from Visit. Okay, so let's see if I have any questions before I jump on to a remote client server sort of thing. Can you show how to access the attributes? So the attributes for what? I'm presuming you are talking about attributes for, so if I create, let's say a pressure visualization, if I double click on it, I get the attributes for this block type. But if I create a slice on it, and I have to click, and this will be wrong, but if I double click the slice, I will get the slice attribute. Is that what you're asking? Okay, I think you already have it. Okay, great. And I think there was another question about, is it possible to visualize a 3D data set stored in an Excel in Visit? Well, yeah. Let's talk about that later. Okay, all right. So let's do something real quick here. I asked you folks to download, this thing called download Visit 3.1.x host profile. Okay, so if you have downloaded it and copied it into the right place, if you're on Linux and Mac, you have to actually copy it into this hidden folder. And if you're on a Linux and Mac, the best way to get there is by doing CD and typing it, okay? Because this is a .visit folder, you wouldn't see it in a file manager normally. So if you go there, you will unzip it and put your files there essentially, okay? And on Windows, you can do that. And if you did this after restarting Visit, you want to restart the Visit application because it will only read these files at the runtime when it starts. If you added them as Visit already started, it wouldn't know about them. So make sure you have that. And then I'll show this to you quickly here. I'm going to close everything. So I'm back on Scratch screen. I'm going to go to Open. So far we ignored one part here when we opened the files. The host was localhost. We didn't even pay attention to this. But if I pull this down, see I have few other hosts available. You may not have this many, but I have few more. We have a host called SDSC expands Visit 3.1.x -tutorial only. This is the one which you are going to pick. And then it's going to prompt you for your username and password. So let me walk through the setup first before we get this far. So if you go to options and go to host profile, when you run Visit, you should see something like this. If you don't see these two things in there, that means those files are not quite there what they need to be, or you need to restart Visit. You have to unzip these two files in these two directories on whatever operating system you are on. When you go to these two files, there is some difference between the two. This one is only good for today, and we'll change some things here. And so in the tutorial only host profile, you will type in your XDR/TR username, which you have been using for your Summer Institute. This is your username. This one is mine. Then you go to launch profiles. In launch profiles, then you will go to parallel here. In parallel here, you should type in CRL 155. I suspect this is already the case. Then in advanced, you will type in these two things. I'm going to put these on Slack. And if you can copy and paste it there. And this will essentially get us into the reservation. So our jobs will run quicker. So you would do -- reservations equals SI 2022 day 4, all in capitals. And -- QOS equals normal -EOT. You would add this. And the way I did this was, let me walk it from the top. I went to tutorial only, I made sure my username is right. Then I go to launch profiles. Then I go to launch, make sure the bank account is CRL 155. Then go to advanced. And in advanced, I'm going to check on the launcher arguments and add these. Once I have done that, I'm going to click on apply. And then I'm going to go to options and save settings. Otherwise, these will disappear the next time you run visit. And just for good measure, we can make sure that, you know, our non-tutorial host also has our own username. So you should change it to your username so you can use that later. Okay. So we have that now. Okay, I have to stop sharing my screen for a moment so I can grab the password. And then I'm going to share my screen again. Okay. Can you guys see my screen?
Yes, and Amit, when you get a minute, there's some questions in the help desk
Okay, let's see.
about locations.
Help desk, okay. Oh, that's very good. What is the link to download that last folder? Oh, it's on the repository, so let's put it here. So here we go. Okay. Now let's go here. Okay, so now we are going to go click on open. And instead of localhost, I'm going to choose the host profile which says tutorial only. And I lost my password now, so I have to grab it again. Okay, I entered my password. Okay, this was way too quick. So I'm going to see if I can. Okay, so once you enter your password, you would get something like this. And you would see a folder called data, which we have already copied some of this data which you have been working with here. So we can open up a file this time around. We can open a file, maybe a different one called CT head. And we'll get another dialog box. We didn't get any of this when we were running on local computer. You can just say okay to that. And what this will do is it will go and launch a job for us on Expanse. And when that job runs, it will connect to that node and it will display the data here for us. Hopefully it runs. Uh-oh, some problem. Okay, so I'm going to dismiss this, close out of here, I think. And I'm going to choose a different profile here. Okay, since I'm already connected, it may not allow me to run there. So let's see, compute engine. Okay, I'm on the local one. I'm going to pick this guy. Okay, I'm going to restart with it because I just want to make sure that we are doing the right thing. Okay, all right, so we are here. I'm going to open the file. Instead of tutorial, I'm going to choose the normal one because I know that worked. Okay, I need to put my password in. I'm going to stop sharing for a moment. Okay, and then once I put in my password, I'm going to say, okay, it's going to go in. Okay, I'm back in the right place. I'm going to go and pick on this data, check everything on. This should launch a job for me. I think there's some, okay. There's some issue. Unable to launch open file. Not sure what's going on here. Let's go and check something back. I'm going to cancel this. I tested this last week. I'm going to open noise.silo here in this different directory. See if it works, and if it works, I'll wipe the path. I think it's not going to work. Okay, I think there is an issue. Something is messed up. I don't know why it's adding this QoS, and it's adding the reservation for some reason. Okay, there is. Something going on. Okay, so, all right. Instead of dwelling too much time on this thing, I think the idea is what's going to happen normally is when you open the file and everything, it will basically look like the same thing what you have been doing, like your desktop. You'd be able to do same things. In this case, the rendering will happen on Expanse and it'll ship and show up here. There will be no difference besides just that the computation is happening on a cluster and you'd be able to operate from here. So there is some gotcha here and some setup. We can figure that out, what that gotcha is, and then send you an update. So to use the cluster, one thing which you have to keep in mind is your data needs to be on the cluster, okay? The visit will not move your data from your local computer to the cluster. Your data needs to be on the cluster. You can browse it and open it, but you can save the images on your desktop. That's fine, because the images are already streaming to your desktop, but you cannot move your data through visit to the cluster. You have to do, use other tools like SCP or some other tools to move the data there. So that's number one. And then the other thing to kind of keep in mind is that when you actually launch a job here, you will get this window on how many processors to run, how many nodes to use, how much time. The default time is set to 10 minutes. So if your job is going to take a lot of time, then you will change this time to much more longer time periods so that your job is actually going to be there for you to be able to do the things you are trying to do. Another thing to kind of keep in mind is this will actually create a batch job for you and run that as a script. So this job will only run if there is resources available on the cluster. So there can be some time of wait time based on how busy the machine is. So you can go and log into the SSH to the machine and see how far you are in the wait queue to kind of figure out what's happening, okay? And I think the other question was, oh, if you have data in Excel, can you visualize and visit? Not quite. Visit needs the data in its own format. And so I can post these links, and I think the links may have changed here. So the next question is, how do you get your data into Visit, right? So, and so Visit has a very good, I don't know if these links are still correct, but we can check. Very good manual to get your data into Visit. You have to have your data in a format that Visit understands. So if you see here, there is a guide called Get Your Data into Visit. Uh-oh, I changed this. Well, there is this guide somewhere there. I think they moved to their own website. I think it's gonna be there. So you can look at this guide, and that's typically the next thing that you would want to do. Data input manual, getting your data into Visit. I'll just put this here, okay, in Slack as well. And so since I've been using the main thing, I'm gonna make a note there as well. So there is that guide, and you can take a look at that. It's fairly detailed. It provides you an example in C, Fortran, and Python even to kind of get your data into Visit. So you need to have the data in a format that Visit understands. So I think if your question was if you have a data in Excel file, you can get into Visit. Not really. I think perhaps the easiest way for you would be to look at a format called BOV format, which is a very simple format, and BOV format, and then look at the documentation for that and convert your data into BOV format, and then use that setup to kind of get your data visit. Okay, so we are 3 minutes past our time. If there is any one final question that I can answer, I'd be happy to. Feel free to unmute if you like. Okay, looks like there are no other questions.
Well, the last question that just came into the main room.
Main room, okay, let's see. Yeah.
How silo?
How are the silo files created? Oh yeah, the same idea. So silo, there is a library. If you look at getting data into Visit, you can use that library. It's a C library, I believe, and you can create the files in a silo format. You don't have to create your files in a silo format, by the way. You can write it in a variety of ways. The BOV files tend to be simplest ones. You just basically write your data in a binary format, especially if it's like a rectilinear format, and create a header file in ASCII, which describes the data, and just load them in if you have data in that format. You'd use Silo or HDF or NetCDF, depending on which domain you are coming from. So atmospheric community uses NetCDF. So yeah, you need to spend some time in kind of looking at what may be the best format to kind of translate your data into. I suggest getting onto the Visits mail list. They are very active. The developers answer questions routinely. Tell them what you are trying to do and ask them a question on what's the best format for you to translate your data into, and you should get a response pretty quickly and kind of getting you a good idea on what would be the best format to kind of you to translate the data into. Okay. Hopefully you folks learned a thing or two, and you guys are enjoying the Summer Institute and finding it useful. Well,